delay again. We're having a little grief with the computer. First, let's begin with questions. Any? Okay. Yes.
Will we have any reviews during the RR?
Yes, I'm sure you will, at least from me, and I think the GSIs as well. I should have put that in my last email to you, and I will announce it again. Yeah, I intend to have the lecture times continue exactly as they have been, with just review sessions. You bring in questions or whatever you want to do. And I might not have office hours. It's sort of doubling up the same thing. But this will be like a giant office hour, those 3 hours. So that should hopefully be good. And I think the GSIs will also be available. Right. That's a good question. Thank you for that. Any other? Okay. Well, what I wanted to do was first to mention some things about quantum mechanics that it's nice to know, because it seems very strange, especially the wave mechanics part. We get all these wave functions of doing wiggles and shapes and all that sort of thing. But let me assure you that when the people who were inventing this in the 1920s, they relied very much on classical mechanics, because classical mechanics works very, very well. And they knew that. For example, they were able to predict, and we do predict, for example, eclipses of the sun. We can predict the path of the moon such that it will pass in front of the sun, and they can tell you to the minute when the next eclipse will occur and where it will pass over the surface of the earth. So people go there and they want to see the eclipse. They know when to go and when to get the hotel reservation and when to get a plane to leave and all that sort of thing. It's really fantastic what classical mechanics can do. Same kind of theory, like orbits of masses around other objects attracted by various forces. And that works extremely well. You build bridges, we understand electricity and magnetism. Things work very, very well using the classical ideas, Maxwell and all that. And then you have the other side, which says, well, matter is really a wave. So what is this? Is the moon a wave traveling in front of the sun and that sort of thing? And in fact it is, but it may not matter so much that it's a wave. But when the people were inventing quantum mechanics, whenever they were in trouble trying to understand what to do next, they relied on the classical ideas, which they knew very well, in order to set up the new theory. So that, in fact, the new quantum mechanics, if you look at it, or I don't know which way to look at it. If you look at classical mechanics with blurry eyes, you sort of see quantum mechanics. Or if you sharpen up quantum mechanics a little bit, you can sort of see the classical mechanics picture coming through. How are we doing?
Down there.
How good of us. Okay, maybe we'll get that finally. It's still copying. So, for example, the wave functions of hydrogen, for example, they look very strange. They look very unclassical. Someone has taken all the chalk, too. So I know there's conspiracy, so I bring my own. We've had a very strange time this semester, I must say. Nothing seems to work as it's supposed to. I don't know what it is. Perhaps it is. It's the Mac and other things. The chalk is gone. Every week we come in with a new set of tricks. It's kind of fun. But anyhow, we'll manage. So here's the thing with various colors. So Bohr said that what you have is a more pictorial thing of an electron going around a proton, and that's a hydrogen atom, and it looks like the solar system, and we can sort of see what it is. Now, wave mechanics comes along and says, no, that's not quite what's going on. We have a wave function, an R function, which is sort of an exponential, R over some distance, where this is the distance, and there may be some kind of average radius that it's having. So that looks very different. First of all, the electron, and that R, by the way, is supposed to tell you where the electron is. And it seems to say that the electron is most likely at the origin. This mode picture here says the electron never is at the origin. It never hits the proton. It's going in an orbit way out there. So how can these be reconciled? Well, the point is that what we've said before is actually the probability of where you'll find the electron is a volume element, 4 pi r squared dr, that's a volume element, times this r squared. That'll tell you the radial thing. Now, when you do that, the picture gets a little different. This is the r function of r for the 1s state of a hydrogen. When you multiply by the 4 pi r squared dr factor, which looks like parabola in r squared, right? It looks something like that. In fact, it's 0 here. You multiply this times that, you get a curve that looks like that. Okay, so that's the probability of finding the electron with respect to the nucleus at 0 here. So, and in fact, the peak probability comes out where Bohr said this electron would be orbiting. So we're getting a little resemblance here. It's fuzzier. As I say, if you look at this picture fuzzy, and that blurs out on you, then you sort of get to the classical, you get from the classical to the quantum. And that goes on even more, because I'm trying also to demystify all those quantum numbers that they talk about. You had in the hydrogen atom, you had your N, you had L, you had M, you had S. Now, what are those about? What's the classical idea behind those? There should be some. Okay, well, the answer is that N, let's do them one by one. N has to do mostly with the radial wave function. And so this, for example, is the 1s state. So you have N is like, for example, the N equals 1. You have a radial wave function like this. Now, and this relates tells you mostly the energy of the atom. Why? Well, the energy, the potential energy, was minus, you recall, the Coulomb potential energy of two charges, epsilon naught over r. So you see the energy, and this is part of the Schrodinger equation. We have the kinetic energy, and they tend to call the potential energy U. So you'd have this plus the kinetic energy, and that was the total energy. Now, the kinetic energy is just a derivative. It's the waviness of the function. And it doesn't depend on the potential, but the potential here depends on R. So then it's not so surprising that the radial wave function is the one that determines the energy mostly, because it's telling you how far from the nucleus the electron is. So this predominantly determines the energy. And for example, in this picture, it's saying that typically the energy here will be something like E squared over this Bohr radius, we're calling it A0, and you get, your usual 4 pi epsilon naught, and maybe a little factor or so in here. Actually, the factor is 2. So the total energy really depends on the distance of the Bohr radius, but it's a radial thing. In other words, the energy doesn't change much as you go around the particle, right? That's not going to change the energy much. especially in a circle. Or in any case, no, actually it doesn't change at all. If you're in a central potential, you can do all kinds of strange orbits and still keep the energy constant. But it is in a circle at any rate. It's going to depend on R. Okay, so N is that quantity. What is L? Well, there's the other quantity that's important in isolated spherical system, and that's the angular momentum. And that is also conserved. Energy is conserved too. So the angular momentum in classical picture is the usual R cross P. So it's a distance from the center, R, and your momentum, mv. Okay, so what's the analog there? So you see, it's something that's going around the nucleus. So you would sort of think that in quantum mechanics, if we're talking about angular momentum, we're going to be talking about shapes that sort of go around the nucleus, not in and out, but around. And so you get these other functions. Well, the easiest one is the one that comes with the 1s function, and that's sort of when L equals 0, no angular momentum at all. You just get the electron traveling all around. Basically, the best way to think about it is traveling in and out through the nucleus, and has no angular momentum because R and P are in the same line, and so a cross product will be 0 for L equals 0 if you have no angular momentum. So that would be, classically, it would be a very elongated orbit. You might have an orbit that looks like an ellipse, but it's very narrow, so that when you're going by here, the R is very small, although the speed might be great. So to make sure that it's actually 0, you have it pass right through the nucleus. Now, that is a very hard thing to grasp, but remember the correspondence principle that when you're dealing with small quantum numbers, that the behavior doesn't look very classical. We're dealing here with the smallest quantum number, and the behavior is very non-classical. So something passing right through the nucleus without bumping it is non-classical. But as the quantum numbers go up, let's say you have a little more angular momentum, like 1 unit of h bar, then the wave functions look different. You're familiar with the p states. L equals 1 is what we call p states. And now you start to see something that looks a little more like the classical, of something going around, because the p states, if you recall, are dumbbells looking things like this, in the z direction, say, and then you have dumbbells in the, let's call this x, y, let's call this x, and let's call that y, and so you have dumbbells in the x direction, and you have ones in the y direction. Let's get some other color. Yeah, now why would this look like an angular momentum? Guys looking like this and like that. You've seen those before, right? You've seen those pictures in chemistry many times. Okay, so why does that look? So now again, we know that the wave function is trying to tell us where the electron is localized. So electrons in this, what we have called you have called in chemistry the pz orbital, they're more or less going more or less in this direction, right? They're sort of localized along the z-axis. So if that has an angular momentum, the angular momentum is sort of around like that, because the electron is sort of in that space. So this has an angular momentum equal to 1, but the projection, or the actual direction of the angular momentum, being perpendicular to the plane here, is perpendicular to the z-axis. That's our z-axis. You see, so this we call m equals 0. That's the projection. M is the projection on the z-axis. And you can see why the pz orbital, if you fuzz your eyes on something like this going around in the z direction, and it's having its angular momentum in that direction, you fuzz it out, you can sort of see the electrons going like this. Now if you fuzz out, let's say you had an orbital electron going around in a plane like that. I'm thinking in going in and out of the board with its angular momentum now in that direction, L in the z direction, its projection in the z direction, m is equal to, in this case, we'll call it 1. But you see, these electrons here, the red ones going around like that. So they're going around in a plane like that. And so their angular momentum is this way. It has a definite projection on the z-axis. So if you look at that in the right way, with bad eyes, you can see where the wave functions do correspond in some way to what the classical picture would do. So I just point that out, that they're really not, they're far apart in the assumptions. The other thing that the assumption is here, that the angular momentum can only take specific directions. It can't be anywhere. In other words, if you have a particular axis produced, say, by putting a magnetic or electric field in that direction, that the angular momentum can only be have projections of integer values on that axis. That's a quantum effect. In other words, it can't be anywhere. If you measure it, you'll find it's either here, let's say it's this wave function here, the L equals 1 state. You'll either find it with a projection of +1, a projection of, now, actually I've got the colors wrong here. The yellow one is perpendicular. Do it here. So if this is my z-axis, the yellow one would be this one. That would be the m value. The projection is 0. Or you can have a projection of 1, m equals 1, or you could have this. This is what quantum mechanics does that's peculiar. And that's, again, this is because these are really waves, and only integral number of wavelengths are allowed, and so you end up with integral values. That you more or less have to feel from what we've done before. It's not, I'm not going to write down the equations that you solve to get that, but as I say, it's very similar to the same reason that you get particular radial wave functions, you get particular angular wave functions. And my only point in doing this is that you want to know that there is a correspondence between the quantum mechanical solutions and the let's see if I can call up something here. Between the quantum mechanical solutions and the classical ones. And it goes, and as you go to higher and higher quantum numbers, it gets to look more and more classical. This is, again, what Bohr said is going to be true, because we know at a certain limit of very high energies and very high quantum numbers, you go over to the classical. That works beautifully. So you would think there's this kind of a smooth transition from the quantum to the classical. And as you go down in quantum numbers, things get harder to envision in the classical terms. Well, friends, we're... oh, okay. Let's see what we can do here. So the PowerPoints that I gave talk about that to some degree. The point being that I try to show here that you see, even if you have a very large angular momentum, if you have a smaller angular momentum, let's say this is a, let's see, L equals 2, that's a D state. So n is 3. So you have L can be 2, again quantized is the quantum thing. 3 state, n equals 3 will have L equals 2, L equals 1, and L equals 0. And the orbits change their shape. And then the m values are just a question of the tilt of the orbit. For L equals 2, you can have it tilting with a large projection on this z-axis, a smaller projection of 1 or 0 or -1 or -2, which is classically the same thing. You could have different orbits without any field here to distinguish the orbits. They all have the same energy, and they all point in the same direction. But once you specify an axis by some physical means, then they take up integer values with respect to that. And the other place where this is true is that we started out with the Coulomb potential and the energy being 0 at infinity. Recall that. Here was the U. We start out with energy as 0, and we go to negative energy. So as you go up in higher and higher states, the energy goes from negative, meaning bound, to back to 0, which means that the speed, when you finally just barely get out, the kinetic energy, the potential will be 0. The kinetic energy will also be pretty much 0 if you just stagger out of this well. And so that would say that the velocity should also go to 0 as you go to higher and higher states. And it is, in fact, true of the quantum theory that the velocity of the nth state is the velocity of the 0th state divided by n. So that indeed, as you go to higher and higher n values, the speed at which the electron is going around in the classical picture and the Bohr picture all go to 0. So there is, again, this correspondence all through. Despite the fact that the angular momentum is going up, the velocity is going down, which means that the particle is going very slowly around the electron. The electron is going slowly around the proton, but its R is larger, so that the product of P times R so although as you go up in value in orbital in n value, the velocity of the nth orbit is going down, but the radius of the nth orbit is going up. Because you go ahead, the bigger higher orbits, they get bigger and bigger. And in fact, this one is going up as n squared, A0, m, and this one is going down as n, so the n's cancel, so the angular momentum is going to increase as n h bar, which is what we're saying, that the higher orbits have n h bar, because this angular momentum here is h bar. That's the momentum in the ground state, and this is the radius of the ground state. So that is the angular momentum in the ground state, which Bohr postulates to have 1 h bar, so that as you go up, the nth state has n h bars. Let me stop. Keep writing n's funny. Sorry about that. So and that one should be an n also. So as you can see, it is consistent. As you go up, the angular momentum goes up, the particle slows down. It's because it's slowing down, its speed being less, it means its kinetic energy is less. Indeed, it's at the higher energy levels, it actually has less, less negative energy is what it has as it goes up. Okay, so I think I have to stop there, but I think that correspondence is worth appreciating, especially with the angular functions, how they actually look like the classical orbits, especially at the high quantum numbers. Now, let me see if I can call up the PowerPoint on. Come on, fella. Here we go. Nuclear. Now, in nuclear physics, we're not going to do everything in great depth, but I do want to make some important points. Okay, well, in a way, nuclear physics begins with the discovery of radioactivity. People didn't know very much. This is 1896 or thereabouts. And it was discovered in a very interesting way, historically, just mentioned this, that a few years before this, Röntgen had discovered X-rays. He was working with the kind of vacuum tube that I showed you last time, where he shot electrons at a target at pretty high voltage, and he noticed some screen nearby was glowing. And he traced the glow on that screen to the fact that his tube was emitting these radiations, which were passing through the tubes, right through the glass, right through even barriers that he put in the way. He couldn't stop these radiations, and they made the tube glow. And this was a big shock around the world. I think I may have showed you the X-ray picture of Röntgen's wife's hand. I don't know if I did that. Maybe I did that after class. In any case, it was a sensation, and people didn't understand exactly what this radiation was, except it was fantastic that it would pass right through materials. So then this Professor Becquerel said, he tried to figure out if he could make materials spontaneously emit X-rays. And it turns out apparently that his father was a geologist, and he had a collection of rocks. So Becquerel took from his father's collection rocks, put them out in the sun, baked them in the sun, thinking that maybe the sun's energy would energize the things and they would then radiate X-rays. Well, it's an idea. It's something to do, and if you got the rocks, you do it. in the manner of speaking. And what he would do to find this, he would actually, because they knew that X-rays darken photographic plates, sort of like light, and so he would take the rocks and put them on top of photographic plates and see if they expose the plates. And he was frustrated because the rocks he'd leave in the sun didn't do it. Then one day, it was a cloudy day, and he didn't put the rocks in the sun. But he had the rocks in a drawer with some photographic plates. And when he went to look at the plates, they were dark. Now, a more sensible person would have just said, oh, lousy plates, and throw them out. But he didn't. He said, there must be a reason why these plates are dark. So he checked among the rocks that he had put in the drawer with the plates. By the plates had been covered. They're in a wrapper, like photographic film. And one of the rocks, he traced down this effect to one of the particular rocks, which is called pitch blende. And he analyzed what's in the pitch blende. It turns out it's uranium. So he had discovered by this curious path that uranium emits a radiation which can pass through paper and other stuff that he tried, and like X-rays. And they finally analyzed the emissions from these rocks into 3 different types. And this was also a sensational discovery. The 3 different types of the alpha particle, the beta and gamma. They didn't know what they were, so they call them alpha, beta, gamma, like ABC. Make it Greek, it sounds that much smarter. And alpha, beta, gamma. And they figured out what these things were by they saw that if you put a magnetic field here and going, say, into the blackboard, you shoot the particles through, and they're coming from your rock, your pitch blende here, and some of them bend this way, and some others of them bend that way, and some of them didn't bend at all in the magnetic field. And then from 8b, at least the sign of those charges, because you know that the force on these is equal to Q V cross B, and the V is in that direction, B is in that direction. You can figure out the sign of Q. And it turned out, let's us figure it out. Let's see, one bending that way is V cross B. So the V cross B in that direction, this would suggest that this is a positive charge. And the fact that some are bending this way would make that a negative charge. Voila. So this they call alpha, this they call beta, and that one they call gamma. That one, by not being deflected, they assume it's some kind of electromagnetic radiation, which doesn't bend in a magnetic field. So there you go. But it's interesting that I actually looked up Becquerel's Nobel Prize address in 1903, and he raised the point that, yeah, I've discovered this, but I don't know where the energy is coming from. Here I just have a rock that we dug out of the ground, and it's shooting out energy. Where does that energy come from? And this is a quote from his source. The source from which they derive the energy they give off escapes us. Well, 2 years later, Albert Einstein came along, and he gave an explanation. And that is that what you're doing is that from the rock, these alpha particles are shooting out, and the rock is losing some mass. And that is giving you an energy in proportion to c squared. There's where your energy is coming from. And I have here a very simple derivation that of the E equals mc squared, probably the most famous equation in physics. Everybody knows E equals mc squared. And you can derive it in this very simple way, but time constraint will make me move on. So, but you know, this is something we ignored when we did the theory of relativity, but it does come out of the theory of relativity in this respect that we take in this particular derivation. I don't think this is what Einstein actually did, but it's in the spirit of Einstein, in the sense it's a kind of a Gedanken, a thought experiment, where you just have a mass, m1, and you shoot light waves at it. The energy of the light wave is epsilon, say, and we know that it has momentum. This is from Maxwell and relativity, that a light wave has momentum. We've said that it can exert pressure. And you shoot equal amounts on either side, and they are absorbed totally, let's say, by this mass. So that's one point of view. What the Einstein approach to things is, all right, let me shift my point of view. Let me imagine that I am an observer over here, and I'm observing this, but moreover, I'm moving toward this event. Well, that's one thing, but on the other hand, if I think of myself as being stationary, the event is moving toward me with a velocity v. Let's say I was moving downward v. The event is moving toward me, and the waves are coming toward me. So they look like that. And now, if you calculate what this observer sees, it turns out that the only way he can explain his observation is that the mass here will have changed by an amount of the energy that it's absorbed, these two epsilon energies over c squared. So that by absorbing those things, the mass has increased by the total energy absorbed over c squared. That's the gist of that proof. And it explained Becquerel's question of where the energy comes from, although, of course, you couldn't measure the change in mass. Shooting out a couple of little alpha particles, you would never be able to measure the mass. But at least there was a theory to explain that. And, well, I have and you will have a demonstration now in your lab, and you're supposed to be very careful about this stuff when you work in the lab. Don't bring any food because you don't want to ingest this material. And all I'm going to do, I think, is just show you that a lot of things have this, by the way, is a Geiger counter that, as I mentioned to you, Geiger was working with Rutherford. He was the guy behind the screen catching the specks of scattered alpha particles. Do you remember that? I talked about that a little bit? Some of you do. Well, what Rutherford asked his students to do was they took some of Becquerel's uranium, and the particles were coming out. They collimated them. That is, they put them through, as you will do. See, if you have like lead over here, that absorbs very well. So you have a beam. And what they did is put it through a gold foil, very thin layer of gold, and the particles were scattering in all directions. I think I did that demo too. And some of them and they went around with screens to see how many would hit where, and they actually had Geiger and Marsden looking at this to see where they hit, and to see the distribution of scattered particles. And from this, they realized that the gold foil was mostly empty space, vastly empty, but a few particles bounced straight back, more or less, which told Rutherford and his friends that the atom that was constituting the gold foil was mostly empty space, and inside, though, was a little bit of mass concentrated at the center, and the electrons running around outside. So this was the reason that we think we have a nuclear atom, and of course we have a lot more confirmation since. So Geiger invented this electronic device to do the same task of counting particles. And what it is, very simply, is just that you have a plus and a minus arrangement of battery, say, and it's in a gas. The gas is a good insulator, so you get no current flow. But if a charged particle, like one of these plus 2 charges, comes through, it knocks electrons out of the gas, out of the energy levels. See, the electrons are sitting in the gas, and this alpha particle comes in, bumps it, knocks an electron out. This thing becomes ionized, and this is another charge. So the gas becomes slightly conducting, and a little bit of electricity flows across, and you get a click. So a click is one particle causing electrical conduction in the gas. It's a very simple idea. So that's what Geiger did, and we can count on him. So there are all kinds of things. The odd thing is that at one time, they actually made watches with radium dials. Actually, when I was a kid, they had these things around. It was a big deal because you could, the radium glows. They put a little scintillator or some other material on top, and when the radiation comes out, the thing would glow. So if at 2 in the morning you want to know what time it is, why you would want to know, I don't know. But if you do, you could look at your watch, and it would just you could see the numbers and the hands in the dark because it's scintillated. So radium dial is very popular. So I don't know that you really want to do that too much. Also, we have, in your house, you have a smoke detector, and in the smoke detector is the element polonium. Where is it? Looks like it's over there. Or more like over here. Polonium is very dangerous. There's recently been a news story where somebody who was a very strong critic of President Putin was in London, and he mysteriously got poisoned by polonium, and he died. And people are wondering how he got polonium, and they think it's accused, I don't know, but it's accused that some of Putin's agents managed to get some polonium in his tea and assassinated him. So polonium is very dangerous stuff, but you have some or maybe it's americium, I'm not sure, but it's very radioactive stuff. And what it's doing is that when the smoke, if your house starts to burn and there's smoke, the radioactivity from there will trip and cause clicking sound, or make a current flow, and then the sound goes off. Did your smoke alarm ever go off? Everyone? Ever hear smoke alarms go off? Terrible sound. And it's tripped by the fact that smoke is getting in here and being ionized by the radioactive source. Let me stop there. It's enough. You'll be playing with this, but I say be careful and don't eat it. You know what I mean? You don't want to go home glowing. All right. So what else is new? Let's see. Okay, now the other... here's Rutherford's experiment where he has a detector. He has the source, he has the gold foil, and you have your detector over here, which is actually, in his case, it was Geiger and Marsden with the detectors. Although it did hit a screen. And the idea is that most of them go through, you see these orders of magnitude change. That's 5 orders of magnitude. 100,000-fold difference between an angle of 90 degrees and straight and no deviation at all. So you have only 1 in 100,000 particles would go off 90 degrees. But even that, and you could explain that by saying there was a nucleus that was scattering these things. And here's another thing. Another question is, how did these particles get out of the nucleus? So soon after Schrödinger's theory, the wave theory in 1926, George Gamow, who's an interesting physicist, published a paper explaining that the reason, the way the particles get out is by tunneling, wave tunneling. He thought of the particles as being sort of trapped in the nucleus. It's another very nice, simple idea, and we can understand that now. He says the nucleus apparently is a barrier, and you have like an alpha particle, this is +2 charge, and it's sort of rattling around in here, but it's a wave. In fact, he has a very nice drawing, which could almost be put in a book, where the particle, when it comes to the barrier, as we have said, it sort of dies out, and if it has any life at all, at the end, it travels out as a wave through the wall. So was his explanation of how radioactivity occurs. You have alpha particles that are trapped in a nucleus, and they tunnel through the walls. And the probability, as you know, it can be very small, especially if the wall is thin. How big could it be? The nucleus, it turns out, the radius of the nucleus goes as the number of particles in it. Now I have to explain that. Times some constant with the R0 is approximately 10 to the minus 15 meters. Although I have to give you, this is the easiest part of the subject, to define terms here. It turns out that we now believe that a nucleus is composed of protons and neutrons, and even these may be composed of other things, but let's keep it at this level, protons and neutrons. Now, if we count the number of protons, we call that Z, which is called the atomic number, and it determines the chemistry. So this determines the chemistry, because it's the number of plus charges. So this is what's attracting other things. The number of neutrons is called big N. It's easy enough. And then the sum of these two, we call the atomic weight A. A equals the atomic weight. So it's the sum of the neutrons and protons. It should be the atomic mass, actually. Let's call it mass, because weight only comes when you're near gravity. Okay, so those are the things. And so those are the basic definitions. And the other thing that you want to be aware of is the only real math in this. Well, there's two pieces of math. One is the decay rates, and that is how rapidly do these particles come out. If you start with a certain number, what we say is that the number will change. You start with a certain number, n0, and what we say is that the change in that number will be proportional to the number that you have, which is a very reasonable assumption. This is a decay equation. If I have 10 atoms, maybe one will decay in an hour. If I have 100 atoms, 10 times more, maybe 10 will decay in an hour. So in an hour. So the number that decay in a unit time is proportional to how many you have at that time. Without too much calculation, you can come up with the fact that